I'm Mackenzie Farnell, and this is my MSc 260 Thermodynamics of Materials course project. Today I'm going to tell you how to solve a problem in chemical engineering. So I'll start by reading the problem to you. A turbine takes 5,000 kilograms per hour of water vapor at a pressure of 4,000 kilopascals and 300 degrees Celsius. This vapor enters into the turbine at a speed of 60 meters per second and is later discharged at 200 meters per second at a position 3 meters below the entrance of the turbine. The turbine generates 570 kilowatts of power, and heat losses are estimated at 135 kilojoules per minute. A small portion of the vapor discharged by the turbine passes through a valve, which releases the vapor to the atmosphere. So we have three questions. What is the temperature of the vapor at the discharge valve? Calculate the quality of the vapor at the discharge valve if it is humid. And with this information, is it possible to determine the thermodynamic state of the vapor at the discharge of the turbine? So with this, we're going to start by setting up the problem. So there are 3 points to kind of think about. The point where the material enters the turbine, we'll call that point 1. And then there's a point where the material comes out of the turbine, which we'll call point 2. And the point where it enters the valve, which we'll call point 3. So you'll recall one of the questions was to calculate the quality of the vapor at this point when it's entering the valve. So to calculate that, we need the specific enthalpy minus the enthalpy of the fluid divided by the enthalpy of fluid minus enthalpy of gas. So we'll get HF and HG from a table, and we need to calculate H. And since we're calculating the vapor quality at this point, we need to find H3. So H3 is going to be equal to H2 because there's nothing that will change the enthalpy between the steam leaving the turbine and entering the valve. So what we need to do is find H2. So what we're going to do is we're going to find H1 from a vapor table, and then we're going to find the change in H from the steam entering the turbine to it leaving the turbine in order to find H2. And then there are some other values here regarding the setup of the problem. So we were told that the mass per hour was 1.3889 kilograms per second. The work per hour was 570 kilowatts. The heat was 2.25 kilojoules per second. And when the steam was initially entering the turbine, it had a temperature of 300 degrees Celsius and 4,000 kilopascals, and it was entering at a speed of 60 meters per second. It then lowers, the turbine entrance is then 3 meters below the entrance point, and the steam comes out at a velocity of 200 meters per second. So we'll need all this information to solve the problem. But to find the change in enthalpy, we're going to use the first law of thermodynamics. So that's shown here. The first law of thermodynamics is just the law of conservation of energy. So it says that the heat minus the work should be equal to the change in internal energy. And so the change in internal energy, delta U, is equal to the change in enthalpy, that's the value we want to find, plus the change in kinetic energy, plus the change in potential energy. And so we can find the change in kinetic energy and the change in potential energy. And we have this mass, work, and heat, so we can solve for the change in enthalpy. So for the change in kinetic energy, kinetic energy is equal to 1/2 times mass times velocity squared. So since we multiply by mass in this part of the equation, we're just going to calculate 1/2 times velocity squared. So the final velocity was 200 meters per second, and the initial was 60 meters per second. So the change in kinetic energy will be 1/2 times 200 meters per second squared, because that's the final kinetic energy, minus 1/2 times 60 meters per second squared, the initial kinetic energy. And we get that the kinetic energy is 18.2 kilojoules per kilogram. Next, we want to find the change in potential energy, which is equal to mg delta H. Once again, we multiply by m in this part of the equation, so we just need to find gh, where g is gravity and h is height. So g is 9.81 meters per second squared, and the change in height was 3 meters. So the change in potential energy was 0.02943 kilojoules per kilogram. So now that we have all these values, we can rearrange this equation to solve for delta H. So rearranging, we see that delta H is Q minus W over M minus the change in kinetic energy minus the change in potential energy. So we plug in all the values that we found, the Q, W, and M from the problem setup, and we just calculated the change in kinetic energy and the change in potential energy. And once we plug that into our calculators, we find that the change in enthalpy from point 1 to point 2 is minus 427 kilojoules per kilogram. Okay, so now in order to find the enthalpy at point 2, which we're going to find, we need to find the enthalpy at point 1, and we're going to do that using a table. So we know that the pressure here is 4,000 kilopascals, which is equal to 4 megapascals, and the temperature is 300 degrees Celsius. So going to this table for superheated water, we read it by finding the pressure, which is listed at the top here in these areas, and then we look at the temperature, which is listed along the side, to find the enthalpy H. You also know that this table tells you the volumetric flow V, the internal energy U, and the entropy S. So in our case, the pressure was 4 megapascals, so we want to be looking in this box. And the temperature was 300 degrees Celsius. So using that, we can see that the enthalpy is 2961.7 kilojoules per kilogram. There we go. So now that we have H1, we can get H2. It's just going to be the change in enthalpy from points 1 to point 2 plus the enthalpy at point 1. So plugging in those values, we get that H2 is 2,534.7 kilojoules per kilogram. So now we have H, so we need to get HF and Hg, which we're going to get from a table. So we know that it's entering the atmosphere, which means that the pressure is 101.3 kilopascals, because that's what atmospheric pressure is. So going to another table. So this is a pressure table for saturated water. So we go to where the pressure is 101.325 kilopascals, because that's atmospheric pressure. Here we can see that the temperature of the vapor will be 99.97 degrees, which is the answer to the first part of the problem. And then we can get HF and Hg. So we see HF is 419.06 kilojoules per kilogram, and Hg is 2,675.6 kilojoules per kilogram. So we got this temperature from the table, so that's the answer to part A of the problem. And now we can calculate the quality of the vapor. It's just the H we calculated, 2,534.7 minus HF over Hg minus HF. And we got all those values. We calculated this value and we got this value from the pressure table. And doing that, we get that the quality of the vapor is 93.75%. So now we've solved most of the problem. So we saw from the table that the temperature was 99.97 degrees Celsius, and through various calculations we got that the quality of the vapor was 93.75%. So the final question is it possible to determine the thermodynamic state of the vapor at the discharge of the turbine? And the answer to this question is no, because we don't have enough information in order to find the values that we need from the table or to calculate them. So hopefully this was helpful in teaching you how to solve this problem, and thank you.
Hi, I'm Mauricio Luna, and I'm going to explain a problem of thermodynamics materials, which involves the production of white clinker. First of all, we have that the raw material, the white clinker, is 80% limestone, which its chemical compound is this one, and 20% of kaolinite, which is chemical compound is this one. In the first problem, we have to analyze which of the reaction is not likely to happen. We have that the reaction B and the reaction E is not likely to happen because it contains iron, and iron is not part of the white clinker raw material. The The second problem is to calculate the total enthalpy of formation, which this formula is the total enthalpy of formation is equal to the enthalpy of formation of the product minus the enthalpy of formation of the reactant. This is because the reactant, of course, will have a certain amount of energy that is taken from the product, and the remaining enthalpy that is in the system is the total enthalpy of formation. Here we have the enthalpy of formation of each of the reactions, and we serialize the number 2 here because it is important to multiply the constant for the enthalpy of each of the products that has a certain magnitude. In the third problem, we have to calculate the change of enthalpy in each of the reactions considering the amount of sensible heat. For the formula of sensible heat, we have that A, B, and C are constant and T is a variable. Then we have to consider the formula that for the change of enthalpy. The change of enthalpy is N by the integral of Cp delta T. N is going to be the number of moles. That is going to be always 1 because the equation is already balanced. And the lower limit is going to be 298 always because it is the base temperature of the problem. And the upper limit is going to be given by the problem. Then we have to consider and add every constant of the products and subtract the constant of the reactant. We do that in each of the constant A, B, and C. For B and C, we have to multiply by its variable, which is T, and T power minus 2. And then, when we already have this, we have to subtract the enthalpy of, we have to add the enthalpy of formation given by the previous problem in the exercise. With this information, we do the same in each of the problems, and we have these results that are in kilojoules per mole clinker. In the fourth problem, they ask us for the change of enthalpy in kilojoules per kilogram clinker. We just have to convert with the conversion factor given in the problem. We multiply the conversion factor by the change of enthalpy, and we get this in kilojoules per kilogram clinker. In the fifth problem, we just have to add the total amount of change of enthalpy in kilojoules per kilogram clinker, and we have this number that is in these units. In the problem number 7, we have to calculate the amount of petroleum coke used in the process of clinkerization. First of all, we identify the closing mass, which is 30 tons per hour, then the radio, which is 1.55. We divide these two numbers to obtain the amount of mass that petroleum coke has in the clinkerization process in terms of tons per hour. Then we have to identify what is the value of calorific value, which is the amount of heat produced in a process of combustion under normal conditions. This value is 35 megajoules per kilogram. Then we have to multiply the amount of mass that we previously obtained by the amount of the sum of the change of enthalpy that we already have from the previous problem in terms of kilojoules per kilogram. Then with this result, we divide it by the calorific value of the petroleum coke, and we obtain a value in terms of kilogram per hour, but we need it in tons per hour, so we divide it by 1000 and we get this result. In the problem number 8, we have to determine the phase of Belite under the conditions that the temperature of the reaction G is at 1633 degrees Kelvin. We can use this phase diagram, which is in degrees Celsius, so we have to transform it. The final temperature will be around 1400. And knowing that value, and knowing that the mass in percentage of SiO2 is equal to 32%, we can locate the final phase in this area, which is C3S plus alpha C2S. In the problem number 9, we have to determine the area in which the white clinker operates with this compound. First of all, we have to get this value that are percentage in which the chemical is divided. Then with this percentage and its complement,
we can analyze and draw lines to determine this area. This area will be the one in which the reaction occurs. Unfortunately, we have to consider the reduction in the use of petroleum coke. This is because of two environmental important reasons. First, we have the damage to the atmosphere. In the production of petroleum coke, it is released a lot of carbon dioxide. It is a powerful source of this compound. Second, we have that the particles of the petroleum coke are very small and very toxic to the human body. So, in a long term, it could cause a lot of different diseases.